Welcome to the HC Insider Podcast, a podcast dedicated to the commodities sector and the people within it. I'm your host, Paul Chapman. Today we're talking the pathways for decarbonising transportation across cars, rails, heavy road, marine, aviation. What will these various modes look like in 2050 or 2100? And therefore, what are the bets companies and executives need to make today in terms of infrastructure, fuel supply, and the equipment itself? To talk about this and take each mode one by one is Michael Barnard. Michael wears a few hats related to decarbonisation of our global economy, but crucially and uniquely has been focused on this very subject for over 15 years. He's the chief strategist at the Futurist Electric. He sits on startup advisory boards. He's simulated airport electrification through his firm Distance Technologies, and he projects major decarbonisation trends decade by decade in his prolific publications. I'll include notes to his publications in the show notes, and while this episode is a long one, I think you'll find it fascinating. As always, you can really support the show and support getting guests like Michael through leaving us a positive review on the platform you're listening on, particularly Apple and Spotify. It will take you a moment to leave 5 stars, or it will take you 2 moments to write a quick note on what you like about the show and help us broaden the audience. And finally, as always, I hope you enjoy the episode. Michael, welcome to the show.
Paul, glad to be here.
Fantastic. So we're talking pathways for decarbonising transportation. And we're using quite a long time horizon here, 2050 and even beyond. And this is a key topic because today bets are being made, money invested, lobbyists deployed on the various pathways, because whilst we know in some sense we have a view of where the end point will be, we don't know which pathway it's going to take, and it's very much pathway dependent. So we're going to go through each of the different transportation methods and draw on your very long-term focus on this issue and get some of that expertise from you on where you think it's going to go. Before we go too far, just set the scene for us. How immediate, how urgent are all of these transportation sectors and verticals feeling the pressure to decarbonize?
Feeling the pressure is an interesting one. I mean, to be clear, we have to decarbonize transportation. The biggest problem is ground transportation. It's by far the largest consumer of fossil fuels and burning and creator of CO2 as a result in transportation. Everything else is smaller, but non-trivial. Aviation globally is, depending upon how you count it and what you count in, it's like 2 to 5% of global CO2 emissions. Marine shipping is in the 3% range, so it's in the same range. But it's ground transportation that's the big hitter in transportation. And there's really good news there, and there's good news in aviation and shipping too. So as we consider, net zero by 2050, which is the focus of a lot of organizations, a lot of what we're trying to achieve, and the focus, by the way, of the new U.S. transportation blueprint that came out in January, by 2050, we have to have resolve most of this stuff. We have to cut a lot of those CO2 emissions. And that's, 27 years from now. If you consider the lifespan of a car, it's increasing in the United States. It's about 12 to 13 years on average. So a new internal combustion car purchased today, or, an Escalade or something, is likely to be on the road for half of this duration. Similarly, airplanes, well, those airframes, they last for 30 years, 40 years in service before they, are no longer certifiable and are decommissioned. Freight train engines, some of them some of the diesel electric hybrids from the 60s and 70s are still running, and for a variety of regulatory reasons are just being refurbished. And so we have these capital assets and these transportation assets that last for decades, and yet we need to be at net zero by 2050. So there's a real challenge there that we have to think through, and it's part of the problem with transportation. It's not like just compare and contrast something that doesn't last very long. A new flat screen TV might last 5 years. These things last longer. So that's the big problem. We have to square that circle.
And just broadly speaking, you've kind of got the twin pressures of regulation at the state level, at the country level, and at the European level, and even potentially the global level. You also have customer preferences driving these choices. Is I mean, is every transportation OEM, they're having to tackle these things straight on at the moment, or are there sectors of the slices of the sector that are just like, this currently doesn't sit in our reasoning or whatever it might be? I mean, how top of mind, how in the boardroom are these discussions that we're about to embark on about right now?
Well, it depends on where you are in the world. So let's just compare and contrast. A lot of transportation's issues deal with, how commerce and people are laid out. A lot of the discussions that we hear, because we hear the English language press and the English language analyses, and the majority of those come from the United States because the United States loves gazing into its navel and telling everybody what it sees. As a reason, any data you want about anything, the United States has published it and it's publicly available. It's a remarkable resource. But the United States is an outlier in many ways. And so we tend to get an availability bias. I have great conversations with brilliant energy analysts and people working to decarbonize stuff like Mark said, Jacobson and Bill Nussey. And like many people in that category, they live in fairly large detached suburban homes with big lawns, big roofs, and garages. Well, that's about 0.8% of the world's populace lives in US suburbs. And of that 0.8%, well, 20% of people who live in US sprawling suburbs actually live in multi-unit residential buildings. If we go instead to the rest of the world, 90% of people in China, for example, live in multi-unit residential buildings. Detached homes and sprawling suburbs are prevalent in the United States, very prevalent in Australia, and provinces of Canada like Alberta, Edmonton and Calgary are quite sprawling as well. So we have to say the geography matters and the pattern of development. Like Canada's cities are much denser than the average for United States cities. So even despite having fewer people, we actually have on average greater population density and different transportation problems. And then we get to the problem of transportation within a city and transportation between cities. And so we have to think about how do you get between, Philadelphia and Boston or Toronto and Montreal? What are the modes that are available to you? How do you get freight between them? How do you get people between them the most efficiently? And that varies as well. So United States is a bit of an outlier. I just did an analysis. The U.S. transportation strategy blueprint is top of mind for me as I just published 2 substantive analyses of it. I finished and submitted them today, and one of them's live. And I did a bunch of work on global rail patterns. So just to take the rail one as an example, India has a major geography and major economy globally, and a very large country with extremes of weather and of geological structures, not dissimilar to the United States. It has 83% of its rail electrified. China has 72% of its rail electrified. Europe has 60% and growing electrified and is increasingly trending to grid-tied and battery electric hybrid models for the places where you can't put in catenary overhead lines. The United States, by comparison, has under 1%. It's probably approaching 0% of its rail electrified.
Mm.
So we kind of look at that and go, the rest of the world has a lot of rail and it's electrifying it as the primary dominant strategy. The United States clearly isn't. So
Yeah.
what's going on there? And so, part of that is that the United States built rail under private robber barons in the 19th century, and private ownership of rail has persisted into the current day. There are about 700 private owners of rail tracks, according to the numbers I've seen, in the United States, and there's twice as much rail per ton of freight traveling the rail in the United States as Europe. And there's 2.5 times as much rail compared to China by the same metric. So American rail is vastly overbuilt and underutilized compared to other major geographies, which actually run more rail over their rail. They run more rail over less track.
Yeah.
That's interesting. You kind of look at that and go, okay, that's a significant differentiator. And the Association of American Railroads is fighting electrification of rail tooth and nail, based on mostly specious arguments, I would say. Because their members, those 700 members, don't want to pay for electrifying rail. And they can't because they don't have much revenue per mile of track.
Because it's
You know,
underutilized. Yeah. It's
yeah,
fascinating though, isn't it? Because then you put your sort of the OEM hat on, right? And a lot of these companies are global. Think of Bombardier, for example, and they've got to sort of create the transportation of the future that fits, these, as you say, very diverse, both in terms of the geographies, but also in terms of the polities and the customer preferences. So again, it comes back to this idea of the big bets that are being made. Do you lean into the electrification of rail and we'll come on to it, battery electric cars and so forth, knowing that these things just aren't going to sell in the US? That aside, okay, so and shout out to Bill Nussey, friend of the show, friend of the HC Insider podcast. Okay, so just before we sort of go through the different modes of transportation, just in terms of the toolkit available, just I guess before we get into a pros and cons, just a brief description. We've kind of got, well, to me it strikes me that we've got, I guess, batteries. There's the electrons and batteries is one, right? Then you've got hydrogen. Can you just give us a very, I know this is a bit of a triggering subject, but just in terms of hydrogen, what do we mean when it comes to transportation? We're talking about fuel cells, we're talking about ammonia. Can you just give us some idea of the toolkit that's out there that people are talking about?
sure. Let's do the entire range. So the entire range for transportation is to, as we think about it, is to switch modes to better modes, rail versus road, for example, water versus road, lower energy modes. So diminishing that. The second thing is electrifying by tying stuff to the grid with catenary overhead lines in the case of rail and trolley buses and stuff, and some freight trucks, versus battery electric, putting batteries, and you can put batteries on trains to get them through tunnels and stuff like that. So that's the shift load to better modes, electrify stuff. Then you've got two primary pathways. One is hydrogen and synthetic fuels made from hydrogen. So you make green hydrogen with electrolysis and electricity and water, and you get hydrogen out, use it directly, or you put it into green ammonia, green methanol, or you build synthetic fuels like synthetic kerosene and synthetic diesel out of it, like Audi's blue diesel. Or alternatively, you let nature do most of the heavy lifting and you use biofuels and you move through the process of fermentation, distillation. Then you do, upgrade them to Jet A kerosene or to diesel. And those are kind of the pathways, so it's electrons directly, electrons turned into hydrogen and synthetic fuels, or letting nature do the heavy lifting and creating biofuels.
So that's an awesome description of the toolkit. We're obviously setting aside potential new technologies that might arise, and we're also setting aside carbon capture, which people are welcome to go and read your views on your various publications. But let's so let's start with and what's fascinating to me about this is the shift in the discussion from, you've been looking at this for 10, 15 years, from 10, 15 years ago, and some people very early on called how it was going to play out, and you've got some phenomenal winners like Tesla that have been way ahead of the curve. But it's fascinating how the debates are still live on a lot of these things, and significant money is still ploughing into one or two of those channels that seems to already be on the losing foot. But let's start with your average car. So where are we at on the debate about how cars, personal transportation, four-wheel vehicles are going to be decarbonized over the next 27 years?
Well, I'm just going to say that the United States transportation blueprint gets this one right. It's battery electric. This is, one of the pure unequivocal wins out of that blueprint. We have a decade of selling electric cars and a decade of trying to sell fuel cell cars. And the fuel cell cars are a flat line along the bottom, and electric cars and electric light trucks are a rapidly accelerating curve upwards. Fuel cell vehicles have to be given away. The Toyota has to give away $15,000 worth of free hydrogen with every Mirai they sell. new or refurbished in order for anybody to buy them. It's that bad. So for light vehicles, we're not going to be using corn ethanol. We're not going to be using biodiesel or biogas. We're not going to be using hydrogen. It's just going to be batteries.
Mm. And why? Because this sets the scene for the future discussion. There's two parts to this. One is, what is it about battery electric vehicles that have so obviously captured both those twin elements of supporting policies, but also customer preference?
Well, it's pretty straightforward. So let's talk about a battery electric vehicle. It has a battery that just sits there. It has some power management software, which just sits there and is computerized stuff and a little, some technology in there, but it's solid state. It just doesn't do anything. It doesn't move. And then it's got a motor, which is basically one rapidly rotating thing, or maybe it has two motors. So it has two rotating things, and that drives the wheels. That's the entire drivetrain. It's absurdly simple. It's absurdly easy to assemble. It's easy to put it, you want to build a new car around it because then you get a maximized skateboard model like Tesla and everybody else is moving towards. But it's easy. And here's the next part of it. Electricity is everywhere. I know where you're sitting, so you probably don't have quite as many outlets and electronic devices, but I bet you can probably see 3 lights and 2 plugs from where you're sitting. And that's true for everybody everywhere in the developed world and in a lot of the developing world, and even in a lot of impoverished parts of the world. So electricity is everywhere. It's easy to distribute. We know how to do that. It's everywhere. And so if you buy an electric car anywhere in the United States or Canada or Europe, it's pretty easy to find somewhere to plug it in. And it's pretty easy to upgrade that place to 220 volts so that it charges a bit more rapidly. And it's easy to get electricity to a supercharger for Teslas or for other high-speed chargers from other networks. The infrastructure for charging is relatively trivial, and the access to the energy source is relatively trivial. And building one of these things is actually quite easy.
Mm.
Making them really good, as Tesla has done, takes a lot of engineering, a lot of effort and money and innovation, and then scaling to selling millions of cars a year takes a lot of money. But the barriers to entry to building electrical vehicles is pretty low, and to charging is pretty low. Let's compare and contrast to hybrid.
Yeah, and people seem to love them as well. That is a really nice segue and stark contrast to why hydrogen has been ruled out and why Toyota is can't give them away. What is it about hydrogen using that same rubric of ease and facility that isn't working?
Okay, so let's talk about the hydrogen, value chain. So first, you have to make hydrogen from something. Hydrogen is all the most common element in the universe, but it's all bonded to other stuff. It's either in water or it's in oil or gas or it's in plants. It really likes to be stuck to other things, and the bonds take a lot of energy to break. Right, so every unit of electricity that you could put into a battery and get 80% in, when you put it into hydrogen, you get 30% out. Right, it's inefficient. And then hydrogen, while it's pretty energy dense by mass, like 2.2 pounds of hydrogen, a kilogram of hydrogen, has as much energy as a gallon of gas, which weighs more. That sounds great, except that hydrogen as a gas is really diffuse. To kind of get 5 or 6 kilograms of hydrogen, you have to compress it to 750 atmospheres, like, the pressure of the air at sea level, multiply that by 750. And that's what we put in fuel cell cars when the pumps are working. And so you kind of say, 750. Well, a good scuba diving compression rate is 200 atmospheres. The compressors in industrial refrigerators, like the ones in grocery stores, are 50 atmospheres or 150 atmospheres for CO2 ones. So that's a high pressure, and that takes a lot of energy too. And then you have to move it. You have to put it in something, and hydrogen is tiny. It likes to leak. So we have leakage problems. But then there's this other problem when you compress a gas and decompress a gas. What happens is there's a massive change in temperature. It's one of the problems with hydrogen is as you compress it, you have to deal with that thermal change. As you decompress it, you have to deal with that thermal change. One of the problems with, fueling hydrogen cars is you plug the hose into your special adapter in the hydrogen car, the thermal management is off, and all of a sudden you've got a hydrogen hose welded to your car with ice, and you can't get it free, and you can't touch the hose because it's like really cold. um, so this is one of the failings. Like in South Korea, for example, they've got 15 hydrogen pumps in the world. I did a little math, and they have 10 failures a year per pump. It's not a reliable technology, and it's problematic. So that's just getting it there. Now, those pumps, to get to 750 atmospheres and to have a tank that can contain like a gas tank, if you go considering a gas station model, replacing the pumps, well, you have to have an underground tank or above ground tank that stores enough hydrogen, and that's compressed. And then you have to have massive pumps that can keep it compressed and compress it further to go into a car with sufficient density. And that combination is about $2.5 million for a hydrogen pump, as opposed to maybe $100,000, $200,000 for an equivalent gas or diesel setup, and $250,000 for an entire supercharger placement area with like 5 or 6 chargers. So the costs of setting that up to get that is problematic, and sometimes it doesn't work. Oh, and by the way, those pumps are noisy, so they're not good neighbors for anybody. And then we get the car, right? The car then has this 750 atmosphere gas in it, and it needs to be transmitted through hoses to a fuel cell. A fuel cell is a complex bit of tech, and it's solid state, doesn't do anything, but you have to pump it. So once again, moving parts in the stuff. And guess what? The pressure is changing. If you put 750 atmospheres of hydrogen in a fuel cell, the fuel cell would explode from the pressure. It would just blow a gasket. So you actually have to depressurize it. And guess what? That means thermal management in the thing. Then the fuel cell finally generates electricity, and it creates two things. It creates water, and it creates electricity. And electricity goes to the same motors that power electric cars. And some of it goes into a battery, because most hydrogen cars actually have a battery as well. They're really hydrogen battery hybrid cars. But the water, that means you have to then pump the water out as well. So it's a much more complex set of technologies that take up a lot more space inside a car. It takes up more space than a normal internal combustion comparative, gas tank pumps engine with all this stuff, which means you actually have less interior room in the car, and it weighs more. Generally speaking, one of the things we all love about electric cars, for those of us who have driven them, it's like, 3 seconds to 60. Wow, that's fun. Fuel cell cars, generally speaking, because of the way they're structured, it's more like 8 seconds, which is, not as bad as a 1980s Lada, like 13 seconds, but it's still you're not going to write home about the acceleration of fuel cell cars. You're not going to see them winning drag strips and, against customized beasts down in Florida or anything. And so there's that complexity. And then there's the next bit, all that cost of building the hydrogen, putting the hydrogen in the tank, in the gas station, pumping it, and then doing all that stuff means that hydrogen is a lot more expensive per unit of energy. With a Tesla, you can get, with a 100 kilowatt battery, you can get 500 kilometers. So it's a 100 kilowatt hour battery, that's 300 miles. So it's, okay. So 30 kilowatt hours for 100 miles. Pretty reasonable. And a kilowatt hour costs you, from, depending upon when you charge it, from 7 to 20 cents. Right? So this is dirt cheap moving your car around. Well, hydrogen at retail in California has peaked at $18 a kilogram, which is like the equivalent of $18 a gallon of gas. Now, it's more efficient to use because the fuel cell is more efficient than an internal combustion engine, but it does mean you're spending a lot more money to drive the same distance with hydrogen than you are with a normal gas car, and you're spending vastly more than just using the electricity. So that really simple electric car with ubiquitous electricity versus the really complex hydrogen supply chain with really expensive energy and the thermal management problems that fail. And guess what? Maintaining an electric car is a lot easier than maintaining a hydrogen car too. A lot more things to go wrong on hydrogen cars. So that's kind of the separation. We get much more expensive energy that's much harder to use, that has many more failure conditions with hydrogen than we do with batteries.
Yeah. And what an excellent exposition on a culmination of many discussions that we've had on this podcast, put very succinctly. So taking cars and moving to heavy road transport, trucks, etc. Uh, I hesitated to embark on this in a week when Nicola came out with some pretty dismal guidance that's worth reading for anyone interested in this sector about the challenges they face. Where are we at in heavy road? Is that still fair game for hydrogen, or what are your thoughts there?
Okay, so let's tear this apart in two different ways. I'm first going to separate shorter distance road, but heavier vehicles, from long haul trucking, right? So 500 miles and less, 500 miles and more, buses, and 60% of all freight of all trucking is relatively short distance. Like you go to LA, there's a lot of trucks that just drive around LA all day, and they're not driving 1,000 miles; they're driving 80 miles. And buses, do start stop at low speeds, and they have maybe 120 to 160 miles they travel in a day. Right. So that category of stuff, I think, is worth separating from the long haul trucking for a couple of reasons, because that's very similar around the world. Everywhere you have a city, you have buses, you have garbage trucks, you have local delivery vehicles, you have UPS, FedEx, and Amazon trucks, and you have service vehicles and all that stuff. So all of that stuff is electric, no ifs, ands, or buts. And I can tell you why this is true with a very simple explanation. So do you know the author William Gibson?
No.
Great speculative fiction author, Canadian, wrote Neuromancer, which was turned into a movie with Keanu Reeves. Wrote a bunch of other stuff. He has a motto which I've taken on as my personal motto. The future is already here. It's just unevenly distributed. And so, as a person with a global perspective, I've had leadership roles in Latin America and Asia. I've 40 cities on 5 continents, and I have friends and acquaintances around the world. I'm just one of those people. I hit 10 countries by the time I was 10 years old. I'm just one of those people who has traveled a lot and worked a lot and done things like paragliding the southern cliffs of Bali. So that means that when I say the future is unevenly distributed, I always look for the pockets of the future. Where has this played out, and what has the answer been? And so let's just take buses. There are 600,000 electric buses for passengers on the roads of Chinese cities today. 600,000. There are no hydrogen buses. There are 400 to 500,000 electric trucks servicing Chinese cities and Chinese society today. And there are, I think I counted 13,000 hydrogen trucks in the entire country. And so as we look at that, we say, oh, okay, the answer for everything that's in cities is battery electric and potentially some catenary overhead line grid type stuff. Like here in Vancouver, we have buses that have those little overhead things that connect to overhead wires. And that's how they get most of their power. So those are very achievable things. So battery electric and grid tied electric is the answer for everything for the 80% of people who live in cities in the developed world. And so that means that all trucks, most of the semis we see most of the time are doing that. But then we separate out long haul freight transportation. And there we have to get into a different question, which is that the United States pattern? Is that a global pattern? What is it? The United States moves a much higher percentage of its freight in trucks along interstates than any country in the world. The rest of the countries in the world use inland water-based shipping, nearshore water-based shipping, and rail a lot more than driving stuff around in trucks. And there's reasons for that. The United States built the interstate network as a major strategic asset to be able to move military equipment around within the city in the case of an invasion by the Soviet Union, and it had a strategic value. And oh, by the way, then the rail system was all private, and the rest of the world didn't, do that nearly as much. Europe has a lot more rail compared to its road, and has a lot more inland shipping compared to its size. The Mississippi is a huge inland shipping corridor, about the same size as the Yangtze in China, but China runs a lot more inland shipping across theirs, right? That's just the nature of the beast. And so the road transportation problem, the heavy freight road problem, in other countries, it's putting grid-tied catenary lines and battery packs on trains, and it's electrifying inland marine shipping and nearshore shipping. Whereas in the United States, the question is, how do we move trucks from LA to New York? This is an interstate problem. The interstates are huge. They're federal right-of-ways. It's easy to, they should be, if the United States was able to build linear assets, and I talked to Jigar Shah, who's head of the U.S. Department of Energy Loans Program Office about this last year. If the United States was able to have federal infrastructure projects of the scale of the New Deal, we would be seeing HVDC transmission, high voltage direct current transmission, gridding the interstates. Instead, it all has to be locally set up, locally approved, and the federal government can only fund it. They can advise, they can counsel, they can educate, but they can only fund projects that are developed locally. That's just the nature of the beast in the United States. And once again, that's a differentiator from the rest of the world. But in the United States, putting transmission along interstates is trivial. Putting more electricity along interstates is trivial. It has multiple benefits in terms of strengthening the US grid, making more electricity available in more places, enabling transshipment points for rail and trucks to be heavily electrified. That's a logical answer, but incredibly difficult to do in the United States.
Yeah, but globally the answer is, you're saying, I mean, again, it sounds like this is a BEV solution that's sort of staring people in the face, as opposed to a hydrogen solution or even a biofuel solution.
Yeah, and as we move along here, there's going to be some, so the hydrogen solution, it's off the table because every problem with building mega chargers for semi trucks for long haul trucking is multiplied when you say, oh, we've got to build hydrogen refueling station for long haul trucks every couple of 100 miles along the interstates. That's just a massive, massive problem. Remember, 2.5 million for a single charger for a fuel cell car. That's not enough to juice a semi. It's a lot more fuel goes into a semi. So nobody's going to be building that much hydrogen infrastructure. South Korea, as I mentioned, has like 15. Germany is the only country in the world, by the way, as far as I can tell, where you can drive anywhere with a fuel cell car and actually guarantee that you'll be within 10 kilometers or 50 kilometers of a pump for hydrogen. Its history is that. So as we look at it, for long haul trucking in the United States, it's going to be battery electric. The complaints right now are about current battery energy densities, and we're not at the end of cheaper batteries with more kilowatt hours in them that are lighter, right? We're talking about, it's an economic engineering trifecta. And right now, the batteries we can afford to get an affordable road vehicle have a specific weight for the amount of kilowatt hours. But that ratio is changing every year or two. And that curve has been steep for a long time, and curve is not flattening out yet. So in 5 years, 10 years, batteries completely capable, fit for purpose for driving a semi truck 1,000 miles without stopping with 80,000 pound mass are just going to be there. And at that point, every argument for hydrogen just is specious. Now we get to the question. Semi-trucks, semi-tractors are million-mile assets. Basically, they run for 1,000,000 miles, and they're used regularly. So a 1,000,000-mile asset, if you buy a Kensworth tractor today, it's got 1,000,000 miles of road to go in. That's like 8 to 10 years. If we need that to be decarbonized, what's going to go into it next in 5 years and 10 years? And that's going to be biofuels. We have to build the biofuels ecosystem. The good news there is once you get to a certain point, when you're building biofuels, at a certain point, it gets into stuff that the oil and gas industry knows really, really well. As it gets up into the point where you're making biokerosene for aviation and biodiesel, the capabilities of those industries really kicks in. They just have to change their feedstock and go through, get expertise in fermentation and distillation, which many of them are trying to do, and get away from the idea that they're going to do with algae. Algae is weird and tough, and we've got stocks that have everything we need in them from corn. Because that's what modern biofuels are. What I say is there's 8 pathways to biofuels today, and they're all stuff that's waste for the most part. Like right now, we make ethanol from corn, we make it from the ears, in the United States, but we actually have had stock cellulosic ethanol commercialized since about 2013. What that does is you take the ear and you feed it to an animal or human. So they get the corn, they get the calories. You take the stalk, which we'd otherwise burn for the most part, and, just get rid of that way. And you mulch that, you ferment that, you distill that, and then you've got ethanol from agricultural waste. Now, I've done the math. As long as we preserve biofuels for the longer haul segments of aviation and marine shipping, which is my projection, then we have actually enough stock cellulosic biomass from wheat, corn, and rice from current production to fulfill all the needs of biofuels for the world. And then we have 7 other waste streams mostly. Like and there's a UK one that just announced they're taking animal dung and they're turning it into jet fuel. It's just more biomass. It's like, okay, what do we do with this biomass? Well, let's ferment it and distill it and upgrade it to Jet A, and away we go.
Yeah,
we throw away a lot of stuff.
The HC Insider podcast is brought to you by HC Group, a retained search, intelligence and advisory firm focused solely on the global energy and commodity sector. With 6 locations across Asia, Europe and the Americas, and over 50 consultants. To find out more, go to our website, hcgroup.global. There, you can also sign up for our HC Insider content for more interviews and white papers on relevant trends and talent impacts in the commodities world.
I want to end on biofuels because I think that your discussion there and your paper and work on biofuels has been fascinating against a backdrop narrative of food versus fuel, not enough land, all that side. Okay, so heavy, globally we're speaking here, long haul truck transportation on average, on basis, is going to essentially follow the same pathway as cars. We've touched rail, and that seems pretty simple to me that that's just going to be electrified. Most, all new rail is electrified. You've obviously got a very powerful incumbent interest in sort of some of the unique places like the US, where changing over that rolling stock is going to be somewhat challenging and need policy support and so on. But am I oversimplifying just to say that the rail in all of its formats globally, global audience here sat around the world, is just going to end up electrified, and this is kind of the example of the future already existing in most places apart from some archaic places?
Yeah, in the United States, what I'll say is, I'll quote Winston Churchill. I believe it's him who quoted it, might be apocryphal. He says the United States always does the right thing after first trying everything else. And so my assertion is that rail in the United States and its secondary states of Mexico and Canada where I live, who are forced to do what the United States does in this category, we're going to electrify too. It's just, we're not going to do it as fast as the rest of the world. We'll be behind them. It's logical, it's cheap operating costs, and there's a really simple message for the rail industry. If all road transportation is electric and increasingly semi-autonomous with platooning, and hence able to roll longer with lower labor and fuel costs, while trains are running on biofuels or synthetic fuels with higher fuel costs, much more freight in the United States will divert to roads, and all of those people who own rails will have even less revenue per mile, and many of them will go bankrupt. This is a fundamental strategic problem for freight transportation in the United States. The reality of the situation is the rail industry is running into a place where they're going to have strategically very significant problems in maintaining what they're doing, especially as bulk shipping is going to diminish. There's a lot of trains running coal, there's a lot of trains running oil, and that's all going away with peak oil demand and peak coal demand. So the rail industry in the United States over the next 40 years has to transform. If it doesn't transform, it's going to be a withered fragment of itself in by 2050.
Stark outline there. Okay, so you mentioned then touched on shipping. Let's move to marine, albeit that it is a smaller part of the current carbon footprint. This is a very prevalent to the audience listening to this in the commodities world, where most commodities move globally via ship, and lots of bets again are being made on. We've just had IMO 2020. Lots of bets are now being made on ammonia. These assets are even longer lived than those we've mentioned so far. And do you make it ammonia capable? All these things. So let's talk on marine.
Sure. So we have to separate marine into a few segments. There's inland, like short sea or near shore, and then there's deep water, right? So inland and short sea, they don't go very far, and they're always near shore, and they're always near charging. It's really easy for them to go battery electric in a variety of ways, and I'll explain a bit of stuff there. And so my projection is all inland and 2/3 of near sea will be battery electric in the end. It's always going to be more efficient. It's just all the supply chain things that we've talked about for cars and trucks, same thing. More electricity runs into ports, done. And there's something there. The second thing, though, for deep sea, 16,000 tons of resid aren't going to be replaced by batteries in this century. So we gotta have something to move ships across the oceans, and from Argentina to Houston, for example, that's near the shore, but Argentina and Houston are a long way apart, and so that's separation one. Separation two, though, there's actually a really good news story in marine shipping, and that's that 40% of marine shipping today is moving bulk coal, oil, and gas around the world. And with peak coal demand in 2013 and a return to that briefly with the energy crisis last year, peak oil demand per McKinsey, Equinor, and the IEA, probably the second half of this decade, and peak natural gas probably in the middle of next decade, well, then bulk shipping of fossil fuels starts to fall off a cliff in the 2030s, 2040s, and 2050s. We don't actually have to solve a lot for deep water shipping because so much of it is going away, which is kind of the reverse since 1990 when lots and lots of global shipping increased. We're going to actually see a decline in global shipping in bulk. Now, there's two more parts to that story. The second part to that story is that 15% of bulk deep water shipping is raw iron ore, mostly going to the same ports where coal is going. But in the future, there's 2 or 3 things going on. One is we're going to be scrapping a lot more stuff and putting it into electric steel mini mills, like oil tankers, and coal bulk ships, and gas pipelines, and refineries, and internal combustion engines. So we're going to have a lot of raw steel, scrap steel, and we'll supply new steel just by scrapping it and shoving it through electric steel mini mills powered by wind and solar, and get new low carbon steel that way, instead of making it from raw iron ore and coal as much. But even then, when we talk about that deep water shipping, which is going to be biofuels in my perspective, there's still going to be 30% more or double the price of resid. Bunker fuel in ships is dirt cheap waste from oil refineries today. Horrible stuff, which the marine shipping industry is struggling mightily to hold on to as long as possible and pretend they're doing something about. But as we replace it with biofuels, it's probably going to be twice the fuel costs. And that's the best case scenario, because hydrogen and synthetic fuels, same thing, vastly more expensive than biofuels. And that's going to be true into the future as well. We can talk about that at some point. But if it's biofuels and they're more expensive, well, that changes the economics of processing raw materials locally more versus shipping them to be processed elsewhere. And that means that much more of that iron ore would be processed locally. And in the future, processing iron ore requires electrons, not coal. As we reduce iron ore into foamed iron with hydrogen, with green hydrogen, or use direct electric reduction process that's somewhat akin to what we do with aluminum today, we're just going to be able to run transmission lines closer to where the iron mines are, do more processing there, and send, hot briquetted iron in containers, significantly upgraded stuff, not a bunch of the dirt and rocks that come along with iron ore, and just send the iron ore itself to where it gets turned into steel, or we'll actually turn it into steel there and ship, ingots of steel around the world. So a lot less volume of marine shipping for that 15% of raw iron ore. I think it's about 5%. 2/3 of it will go away with those things by 2100. And so we said, oh, okay, so bulk marine shipping is dropping. And the cost means that all bulk goods that are just being shipped somewhere else for processing become subject to the same economics. So we're going to see a lot more upgrading, a lot more containerization. And that has some implications. Bulk ships run around, 8, 9 knots. Container ships sprint across the sea at 23 to 25 knots, which is problematic because that's wasteful, but they're higher margin. But the same, so bulk shipping goes down, container shipping goes up. But container ships, well, they're inefficient running at 25 knots. That's burning a lot of fuel. It's high margin cargoes. But when the fuel is twice the price, the economics say, oh, how do I reduce my fuel use? And there's a whole bunch of levers we'll pull there. There's hypersonic fouling prevention rigs for ships that are commercial products from multiple vendors today that prevent any fouling from starting. There's now robotic fouling, scraping machines in many ports that replace human divers and just basically scrape all the fouling off the bottom of ships. There are the Ulstein X-bow, which is a really interesting innovation in ship form factors, which has a very high front bow that's curved and is much more aerodynamic, and it works just fine for container ships. There are aerodynamic add-ons for container ships appearing. And a big one is just slowing down. If you run at 17 knots as opposed to 25 knots, you're saving an awful lot of fuel. And so what we'll see is the demand for fuel from container shipping will rise because of increased container shipping, but the amount of fuel we use in container shipping will drop by tonnage. We still have to replace it. Biofuels will do that. They're fit for purpose. But once again, it's a lot less fuels for shipping than it is for ground transportation.
Marine seems to be kind of there's still a lot of I don't want to say hope, but sort of noise around hydrogen. You've got vastly bigger plant, vastly bigger distances required, lots more space. I mean, is this whole ammonia as the fuel source, which again is very live in the boardroom of you're trying to think about what your fleet's going to look like in 20 years, you just see no role there?
Well, to be clear, I have a specific opinion, which I think is well supported, which is biofuels will win. But I've also, Maersk has bought a bunch of dual fuel ships that could run on green methanol. They haven't sourced nearly enough green methanol to actually run most of them for more than a half of one trip every year. But, they're betting and doing a bunch of work there. Others are betting on ammonia, green ammonia. And, to be clear, methanol is an alcohol. Green methanol is made from, you can make it in two ways. One of them is a synthetic methanol where you make green hydrogen and then you combine it with oxygen and carbon and make methanol. Another way is biological pathways. Most methanol today comes from fossil fuels. Methanex, the 800-pound gorilla in the market, is actually based in Vancouver, 2 kilometers from where I'm sitting. It's just very close. I was in their office looking at some transformational stuff 6 or 8 years ago. But, we know methanol, and it's, liquid at room temperature, and it's got some toxicity problems that are manageable. But ammonia is problematic in different ways. Like all ammonia today, like all methanol, comes from hydrogen from fossil fuels. It's either coal extraction or, steam reformation of natural gas. This is how we get the hydrogen for ammonia today. And we actually make about 30 million tons of ammonia every year. We know how to do this. And there's ammonia tankers floating around the seas. The thing is, though, right now we use ammonia for fertilizer for crops. And a bit of ammonia turns into a lot of crops because ammonia is nitrogen and 3 hydrogens. And that nitrogen is an essential nutrient for plant growth. So that's kind of a key contextual piece. We already know how to make ammonia. We make it from fossil fuels. In the future, we can say, oh, well, I need ammonia. I can make green hydrogen, which is much more expensive. Then I can assemble it with nitrogen from the air in plants that already do this. And I can make tons of ammonia, which is much more expensive than ammonia is today. Now, ammonia has some other characteristics, and as does methanol. Methanol and ammonia are both about the energy density of fossil fuels. In other words, a ton of ammonia or methanol will move you a third the distance over the sea as the fuels they currently use, which means they need to have 3 times as much of the stuff in much larger tanks in order to achieve that. And green methanol and green ammonia made from green hydrogen are going to be a lot more expensive. Like biofuels are going to be more expensive than current fuels. But guess what? They're a lot cheaper than synthetic fuels. So, that's kind of the thing. It's like, okay, and what about the biofuels? Well, if we upgrade a biofuel to biodiesel, it has actually slightly better energy density than bunker fuel today. In other words, we have the same ships with the same engines running biodiesel, or we can buy completely new ships and rip them apart and put in much bigger tanks to get the same range with brand new engines. Which seems more likely to run a more expensive fuel? Like plug compatible biofuels with the same ships and the same technology, which we know how to run, and they run cleaner, by the way, because biofuels have less extraneous goop in them than fossil fuels. Or we're going to just build completely new ships with dual fuel stuff and massive, much bigger tanks that take up space from paying freight and have different problems.
And it's all connected as well, isn't it? Like, what's fascinating to me about this is like, what you also don't want to be swimming against the stream. If the other big modes of transportation are leaning into biofuels and spoilers, electricity, you presumably all of those associated technologies are getting cheaper and cheaper. And also the ranges are getting longer, the efficiency is getting higher. If you're then betting as being the one mode of transport where green hydrogen is going to be the fuel, or methanol, or whatever it might be, the economics are already against you. Why take that bet? So there is a cascade from cars all the way through all these different modes that has a compounding effect as well, even without getting onto aviation.
Yeah, and that's kind of the reality. And aviation has got a different thing that's fun about that, but it's the same pattern. Why are you the odd person out? Why is the United States not electrifying rail? If everybody in the world is doing one thing, that doesn't mean they're right. But you gotta really question if you're the one outlier. And so then we get to the characteristics. Like methanol has, you got to be careful around humans. It's not good for us. Not that alcohol is good for us, but it's at least pleasant to drink for most people in moderation. But ammonia is a different beast. Ammonia by itself is toxic to humans. You don't really, like if it's there and it's off-gassing, you don't want to be breathing direct ammonia fumes. They're really nasty. But it gets worse. Ammonia, if it interacts with water, a bunch of it turns into a corrosive basic substance, which if you breathe it in rots your lung. It's like breathing acid, but it's a base. It's the other side of the pH balance, but it's corrosive. We actually use hydrous ammonia, which is a specific mixture of ammonia with water in specific circumstances on agricultural fields. But when they apply it to those fields, the people who are wearing it are wearing full body suits, like hazardous materials body suits, rubber gloves, and breathing systems. Because if they breathe it in, when it goes into the field and reacts more with groundwater, it turns into this corrosive substance, and if you breathe it, likelihood of death is high. So that's ammonia stage 1 and stage 2. Oh, and by the way, do boats and ports have lots of water? Yes, they do, right? This is the problem with bunkering ammonia near water and on ships, is that water is just the cost of that mode of transportation. But there is a problem. So ammonia goes through this transformation in the presence of water, and then it transforms into something else, which is also bad for human health. So there's a Netherlands safety officer who's responsible for 3 ports and 16 communities in the Netherlands, something like a third of the country. And he was recently saying, what the heck are you talking about, ammonia in a port? We have bills of stuff every week. If we replace our bunkering for resid with bunkering for ammonia at the same scale, if that breaks and it flows into the port, 80,000 people will die. This is kind of the thing. Now, to be clear, do we deal with ammonia today safely? Do we put ammonia in ships and sail it across the sea today? Yes. But that's as a static load, not something which is flowing through an engine. And it's not bunkered in ports in massive amounts and pumped into ships over water in massive amounts. It's a different kind of thing. Now, a week or two ago, I spoke with Lynn Liu, who's the PhD chemistry from Princeton, and she founded the Ardlinger environmental stuff. But, she was on sabbatical with her family in Singapore when COVID hit. And, as a result, being one of those people, she's now helped found and is running as founding CEO, the Global Center for Marine Decarbonization. She's one of the people who reached out about my biofuels assessment. And what their goal is not to be a think tank. They're not strategists. They are test deployers. They fund projects with their 100 million plus endowment from a bunch of people, including, the big oil and gas firms and the big shipping concerns, big port owners, to test out different things. So they've got a biofuel supply chain and bunkering project, which is, finding some really interesting stuff about ensuring that you actually are getting biofuels as opposed to something else. So the supply chain tracking becomes important. They're doing an ammonia bunkering safety project. And these are multi-million projects. So there's like 10 to 20 million bucks they're spending on each of these projects. And so the ammonia one is focused on, can we do this safely? What do we need to do this safely? And the third one is carbon capture on ships. As I said to her, 2 of the 3 are going to fail, but they're going to be proven failures, and you're going to spend not hundreds of millions or trillion on them. You've spent less, and you'll have proven it, and everybody can go, okay, we don't want to do that. Good enough. It is useful to spend smaller amounts of money to prove that something is not fit for purpose, because people generally don't just listen to people like me and Paul Martin and the safety guy because, well, have you done it? Well, no. Why would I do it? It's a stupid idea. No, well, then if you haven't done it, just go away. We want to do this. It's kind of the attitude that a lot of these things do. But Lynn Liu is, her projects are excellent ways to validate, prove the concerns, and really nail down with lots of money what the viability of these things are. And so the biofuel bunkering thing I think is going to be a great success, find some real value there. The other 2, I think, will prove that they're not fit for purpose. And good. We spent $10 or $20 million on each of these. They're not fit for purpose. Done. But they're not doing the economic assessment that I did, right? It's like a lot more expense, whole bunch of these things. It doesn't pass the economic sniff test.
Moving on, we've just had, it's fascinating sort of how all these things are connected as well. You mentioned Paul Martin, friend of the show as well. On aviation, we've just had Steve Moore of Montana Renewables, CEO of Calumet, on talking about sustainable aviation fuel and pointing to a lot of these challenges on aviation. So can you just, we're running out of time, but can you just talk to us about the pathway for aviation? Are we basically talking the same story here?
In my opinion, yes. So it is the same story. So let's, the same things are being considered. Let's just take hydrogen in its raw form, because people are still pretending that jets are going to be running on hydrogen. Well, hydrogen in its raw form would have to be liquefied. It's like 20 degrees above absolute zero, where people like, 290 degree warmer weather. That's Celsius, by the way. It takes a lot of energy to liquefy it down to that. It has to sit in globe-shaped tanks, and it has to be inside the fuselage. It can't go in the wings, which means that airplanes can't carry as much. And you've got these globe-shaped tanks, 20 degrees above absolute zero. Hydrogen sitting next to passengers, and hydrogen that's that cold. It's like LNG. It boils off. Boil off for LNG is 1 to 1.5% per day. Hydrogen is higher just simply because of the physics, which means you end up with all this excess hydrogen gas just coming out of the thing that you have to deal with somehow. And you don't want it in the fuselage with the passengers. it just doesn't make any sense. You have to radically transform the airframe of the ship to something which is nowhere near what we have today and doesn't fit with how our airports and ground infrastructure are done.
And will take 20 years to get anywhere near certified, right? I mean, we're talking the lead time to get a plane in the air is dramatically longer than any other mode of transportation we've been talking about to date.
Absolutely. The air traffic is absurdly safe, and that's because the FAA and EASA in Europe have been certifying aircraft to have souls in them and not fall out of the sky on schools for decades. And I don't have to think about hydrogen at 20 degrees above absolute zero in the cabin with me when it likes to explode. And I honestly don't think there's a path to certification for hydrogen in liquid form for passenger aircrafts. I don't think the FAA or EASA will look through this.
Yeah, and this has been recognized by IATA, right? Like Steve referenced this in the podcast a couple of weeks back. That actually they're saying in reality, to decarbonize aviation, it is some part electric, some part sort of euphemistically called new technologies. Who knows what that is? But most of it is going to have to be met via offsets, whatever you think of those, and sustainable aviation fuel. And I mean, it's even to the point where this might be the longest tail on hydrocarbons as a fuel source, because you've got this fundamental challenge of the weight associated with batteries. That means long haul flights are going to be really challenged in becoming fully electrified.
Well, so let's talk about electrification of aviation. So I'm actually on the advisory board of an electric aviation startup, Flymax. They're building a special electric airplane for the flight tourism, the rapidly growing flight tourism. I've spoken to electric aviation people around the world, including the CEO of Heart Aerospace, and startups who are doing hybrid electric turboprops with 60 to 100 passengers, et cetera, et cetera, et cetera. Right now, we can run up to 100 passenger turboprops with batteries and a hybrid generator. And the hybrid generator is only, and that's for like 300 mile ranges, 200 to 300 mile ranges. The hybrid planes will only need the generator running for diverting and circling over the target destination airport. In other words, majority of flights will be purely battery electric, right? That's the nature of the beast of hybrid aviation. You just won't use the generator most of the time. It's there for reserve fuel, which is necessary for safe flights. And so we can already do that. We need new airframes for that. They're not nearly as radically different as a hydrogen airframe would be. This is just the characteristics of battery energy density and where you want to put them in the airframe are different. And you just can't replace the fuel tanks with batteries, the wing tanks with batteries, and have it work out the same. And you've got electric routing stuff. You get rid of a lot of the extraneous stuff that takes, in most cases, the exhausts and stuff for the aviation engines. So you can actually get a more streamlined shape. You can have higher aspect ratio wings for the first part, a bit more like glider wings. So there's some changes there. You need to build a custom airframe, but it's very recognizably just a standard airplane. It's just a bit sleeker. It's all composites. It's specially designed aluminum components, which are much lighter weight. There's a bunch of stuff that goes into that. When you're spending $1 to $5 million for a small aircraft, or tens of millions of dollars for a big turboprop, they're high-tech devices, but they're going to look like airplanes and they'll fit into airports globally. And so we're going to see a lot of battery electric emerging in that space. Right now, if you build an aircraft for that, we can do a lot of stuff. And the next piece is the aircraft industry is a hub and spoke industry that's emerged because big turbofan engines have become increasingly efficient. So right now, we've got narrow body aircraft with 2 turboprops or 2 turbofans. And when they're running at 30,000 feet, they're 55% efficient. That's an amazing feat of technology. Stunning. And since fuel is 19% of the average airline's annual expenses, they're all going that way as rapidly as they can change over their plans. What that means is that in North America and Europe, less than 1% of airports do 60 to 80% of all passenger travel. There's 5,030 airports in the United States. And this isn't like grass strips beside somebody's country estate. This is like places that actually have designations and you can fly into. So 5,030 of them, and there's like 60 or 80 of them that actually deal with virtually all passenger transportation. But those 5,000 are scattered all over the country. As soon as you say, fuel is just electricity and maintenance is dirt cheap because it's a simplified drivetrain. Oh, and autonomy is starting to be able to fly cargo along safe routes without anybody in them, as X-Wing is doing. Well, then you start to say, let's activate a lot more of those small regional airports. And let's hop from airport to airport. If I need to go from Philadelphia to Boston, maybe I have to fly one hop in a 4-seater electric taxi and I land somewhere for half an hour to juice it up and then I fly the rest of the way. But I'm flying from a place with virtually no security theater at much lower expenses for the aircraft operator, and I'm doing it on batteries. And so we're going to start seeing a lot of transformation in the industry from the bottom. We're going to see a lot more activation of smaller regional airports in different business models. We're going to start seeing much more, air taxis as a service like Uber emerging with fixed wing aircraft that are battery electric. And we're going to start seeing the smaller turboprop lines, like the 30 passenger, 50, 60, starting to go to battery electric hybrid pretty rapidly as their planes age out. A lot of airframes, for a lot of reasons, are very old. Harbour Air up here does a float plane service out of downtown Vancouver. It's aircraft. It's one of its biggest expenses is getting wrecked beavers and otters to cannibalize for parts and stuff to keep its planes in the air. And so we kind of like look at that and go, okay, so that's the transformation. Then the next piece is there's a bunch of stuff that's going on in this space, including fully electric propulsion systems, which are emerging. And I've spoken to 2 or 3 innovators in that space. There's power management innovations, and then there's battery energy density and lightness innovations, which are going on. I project by, every decade we'll see an increase that's quite substantial. So by 2050, cross-country flights are probably going to be possible for 100, 150 passengers in a battery electric airplane. And by 2060, 2070, my projection is cross-Pacific passenger aviation will be possible. And then it's going to take 30 or 40 years for that to all trickle through. But in the meantime, we're still burning a lot of something in aircraft. And what's that going to be? Well, same question. It's not going to be hydrogen because hydrogen inside an airframe makes no sense and is uncertifiable. We're probably going to want a plug compatible fuel. We're probably going to want a synthetic or biofuel kerosene replacement for the existing fuel for a variety of reasons. Remember, 55% engines. Feeding them something they can burn makes a tremendous amount of sense. But the synthetic stuff's really expensive. And so when we say SAF aviation fuels, sustainable aviation fuels, today we have to ask ourselves, well, what are they? Well, they're all biofuels. Everything that's being certified, we've had certified synthetic aviation or sustainable aviation fuels since I think 2011, and it's all biofuels.
Yeah, they work. They drop in and they work, and yeah, and I mean, what an absolute wrapping up. I mean, what an absolute tour de force. And it is fascinating as well because, as you say, like we end up with the hardest to abate sector, aviation, which is actually relatively, you pointed out at the start, a small percentage, 5%, I think you said, but you're essentially culminating all of these innovations around battery technology and electrification, and also, okay, sustainable aviation fuel at the moment is made in tiny quantities, but that is only going to increase. And then I'll rather than talk, I don't think we have any time to talk about it here, but urge people to go to your papers, and I'll put a link to it in the show notes. There is going to be an equivalent and increasing innovation in biofuels at the same time to meet this demand. And we haven't really said it starkly here. Biofuels, not only are they, of course, not drawing more fossil fuel out the ground, but at least beneath the ground, they're also burn cleaner as well. So It's kind of fascinating when you put it all together, and the bets as you describe it are essentially, if you're focused on transportation today, the pathway is relatively clear, using logic and economics, that it's going to be lean into batteries, lean into electrification, and we're plugging the gap with biofuels.
Yeah, but I'll say this again: we can't waste the biofuels on ground transportation. We have more than enough for the actually hard to electrify segments of aviation and marine shipping. But if we want to run all of our trucks and trains and buses on biofuels, that's a vastly greater amount of fuels, and that's going to eat the biofuel market and just make it really hard to do the rest.
Yeah.
We've got to be really sensible about this. And the reality is, as I like to say, as soon as the spreadsheet jockeys start actually looking at the alternatives, they're going to go battery, they're going to go battery electric. Synthetic fuels and hydrogen.
Yeah, which is going to solve that problem of competition as well.
Yeah, the market will answer this. But, right now we've got like another 7 years probably of idiocy around green hydrogen for energy. Michael Barnard said it recently. It's going to take till 2030 to get rid of the hype, because that's how long it takes to deprogram a cult.
I wonder, and we've had this thread. Another theme of the podcast the last few episodes has been obviously high interest rates typically bring people back down to earth much more quickly than 0% interest rates. So we'll see if that has an impact. But Michael, it's been an absolute pleasure listening to you. We'll put notes in as I said, in the show notes, so people can find your work. It's rare to find someone who's been zeroed in on this topic, is so well connected across all of these different modes, but having focused on it for so long and bringing such a wealth of common sense and expertise to space. So I've really enjoyed it, and I thank you very much for your time.
Paul, it's been a pleasure to be able to share, and I hope your audience finds it of value. And I will just say that there's a lot of choices everybody has to make in the next 5 years to get to stuff that's going to be valuable in 10, 15, and 20 years. I help organizations and investors figure that out. So if you're struggling with a problem and struggling with some choices, reach out to me through LinkedIn, please.
Fantastic. Well, Michael, thanks again.
Okay, Paul, take care.
Thank you for listening. If you enjoyed this episode and want to support the show, please give us a positive review on Apple Podcasts or Spotify. To find out more about HC Insider and HC Group, a search and advisory firm dedicated to the commodity markets, visit our website at www.hcgroup.global. There you can find out more about our services and our offices around the world. There you can also find more content, from interviews to insight pieces to more podcasts focused on the commodity value chains. Thanks again for listening.